So last time we did transfer register functions for the 6502 emulator. This time might attempt some more easy ones, but not as easy as those. The increment and decrement instructions. Some of these are quite trivial, others are a little bit more complicated. So increment X just adds 1 to the X register. That's just got one addressing mode. So is increment Y. Decrement X is the same, it just takes 1. There is the question of what do you do if you subtract 1 from 0 on that? Does it wrap around and stuff like that? I'm not exactly sure. And then these increment and decrement and memory location, slightly more complicated because yeah, they've got to operate on these 4 different addressing modes. But still, they shouldn't be too hard. So I'll start by creating a unit test file. I'll just copy one of the old ones and we'll start again. We'll go for the easy stuff first and then get to the more complicated things. And I think I'll try and do them just like one at a time. I'll try and implement the unit test and then get the instruction working, and then implement the unit test and get the instruction working. And we'll go for it in that way. So let me create the file for the unit test. Okay, so I've just copied an old test here to get going. So let's start with increment X. Yeah, so increment X can increment a 0 value. I don't know if that's what we should do first. So let's just start with that. We'll take the X register as 0. We will have the instruction in X. It's only got one addressing mode again, so there's nothing much to do there. And it expects 2 cycles. And this one will, looks like this will actually be almost the test. We expect the X register to be 1 afterwards. I think that's it. Oh, and there's the unaffected registers. It actually appears to be the same as what we had before. C, I, D, B, and V. Yeah, so those registers are also unaffected by that test. So that looks like a good enough test. Yeah, it takes the X register and it just increments it to 1. So that's pretty good. So let's see what is supposed to happen if we increment 255. What should appear in the X register? Should it be 0? Because it doesn't say it affects the carry flag. You think it might like it'd increment to 0 and then say it's carried. So I wonder if I can find out something more about how this actually works. Oh, in this case though, if this was true, the negative flag, the 0 flag would be set to true. Yeah, so I don't know. I can't find any information on what it does when it wraps. I'm just going to, at the moment, I'm going to say it goes to 0. If I had a real 6502, I do have a real Commodore 64, but I don't have any way to like set it up and break into the program, if you know what I mean, to find out what that did. I suppose we could test it in an emulator, but then we'd just be programming an emulator from an emulator, which wouldn't be a good thing. It'd be like doing the photocopy of the photocopy. It would be better to actually do it on a real 6510 or 6502 and find out what this did. I'm going to assume that this actually just wraps around to 0, and I'm going to write the test for that for now. And if it did wrap, it would set the 0 flag to true, so I'll set that to the opposite to start with. So that seems okay. Is there any other tests I can really do for that one? Is there any way that it would set the negative flag as well? Set if bit 7 of X is set. So let's just test one with the negative flag as well. Can increment a negative value. And this is a bit weird because a negative value would be something with a 1 there, and it could have anything else here. So if I just put a value there, I would expect that to be just have a 1 stuck on the end. Except this time, because this bit is set here, this is negative. So I expect 0 to be false and negative to be true. And I'll set those the opposite way at the start. Yeah, I think I'm happy with those. I'll go with those for now. So we'll just put the instruction opcode in. Where have we got these? These are... What is the opcode for this one? E8. Right, let's see if that builds. Which it does, and I should have 3 failing tests. Which I do. So I'm going to go ahead now, and like I said, I'm going to implement these one by one, and I'm just going to put this one in right now. So this one is increment X. So this just takes the X register and it increments it. It's that simple. We take another cycle for doing that, and oops, cycles, and we set the status from the X register. So I think that makes that pass, which it does. Cool, so that's the first one. So the next one would be increment Y, which is exactly the same test except with the Y register. So I'm going to copy these tests and I'm going to make them Y tests as well. So this is just a total repeat of the first set of tests. So this is increment Y, it's the Y register, increment Y, that is the Y register, and that's the Y register. We could refactor this out, but I don't know. I've not done it. This time I've not done it. And so that should be it for that. Oh, except need to declare that as well. It's C8. Oh, what's wrong here? Oh, once again, test. Right, 3 failed tests. Yes, and we'll go ahead and implement that one. This one gets easier now because it's literally that, but there's a Y, there's a Y, and there's a Y. And I think that's going to make that one pass. So that's the other one. And then we've got the same thing with decrements. So decrement is just, yeah, setting the same registers, and subtract 1 sets the 0 negative flags as appropriate. And the question would be then, really, we want a different test for this one, because what would happen if you decrement 0? We'd expect it to go up to 55 if it's the opposite of the other one. So I'll copy these to start with. I'll copy the Y tests. And let's see what we get. So this is, let's do DEY. Can decrement a 0 value, right? So this is the weird one. So it's Y in there, sorry, 0 in the Y. This is DEY. It's still 2 cycles. We'd expect, I think we expect the Y register to wrap. And then we expect 0 to be false, and I think we'll expect negative to be true on that one because it's set all the bits. If FF's got all the bits set, then that would be a negative value because bit 7 is set. And then, yeah, we don't expect the other registers to have changed, the other processor flags to have changed. So this would be, I can decrement 55. So we'd expect this to go to FE, and I would say that is also going to set the negative flag, and it won't set the 0 flag. Just setting those to the opposite, making sure I do that. Yeah, I think that's right. So we can decrement a negative value. So in this case, we are going to, I'll put the 1 there, make this easier, and expect it to go to that. We expect 0 to be false, negative to be true. It's DEY. So let's see if we can, oh, it didn't change that instruction on that one. DEY. Right, okay. Let's see if this one works, or we can get it to work. 88. So I'm expecting it to compile and 3 failing tests, which I get. And then I can go and implement this one. And again, I'm just going to copy that. This is DEY, decrement Y. Y register gets subtracted, this takes a cycle, and we set the states from the Y. That is too easy. Is it going to pass though? Right, it does. So again, we're assuming we've written these tests right, but with all the information we've got at the moment, that's what we know. So I'm going to say that's okay. And we want the same thing for decrement X. This is, take these last 3 and I'll just do the X versions of these as well. And then we get to the more interesting stuff with all the addressing modes. DX, X, 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 X. So same set of 3 tests, except this time we are going to decrement the X register. So what's the opcode for that one? CA. And 3 failing tests. Decrement X, this one is. Decrement X. So this one just subtracts 1 from the X register and sets the status from the X register. And there we go, that's that one done. So we've done the easy stuff there, but we got ourselves 4 more instructions working, probably. I wonder, what's the next one we want? Decrement memory, that's the one we want. So this one's got, yeah, it's a bit more complicated. We've got a 0 page X version, absolute and absolute X. We've got to make sure we get these cycles right. But other than that, it basically does the same thing. Subtracts 1 from value held at a specified memory location. So I assume that then this is done without affecting the registers, and also it subtracts 1 from the memory, it puts it back into the memory location, and it doesn't affect any of the existing registers. So this would allow you to just subtract 1 from a value in the 0 page. You can see how much more expensive that one is, the 5 cycle version, than if you've actually got the value in the register itself. So even 0 page isn't as quick as the register, unfortunately, because you've got to get that data out of memory. So let's just start a new test for that one. Maybe we can go one at a time with the addressing modes, maybe, I don't know. So we'll go for can decrement a, we'll just do can decrement a value for now, just a value. This doesn't need anything in the X register anymore, and we'll look at those in a minute. DEC. But this one does need some more information. So it needs, the next thing it needs is so 0 page addressing, the next byte would be the value in the address in the 0 page. So let's go for 42 in the 0 page and at 42 in the 0 page. We are going to put the value 57 for some reason in hex, don't know why. We're going to put the value 57, and at the end of this test we are just expecting that the memory location 42 has been decremented by 1, and it should be 56. And we're going to expect 0 flag is false and the negative flag is false. I don't think that 57 is zeroed. So we'll set those to the opposite. Same thing, unaffected. Expect unaffected register. I've called that registers and it's actually flags, isn't it? Yeah, I'll rename that. Well, that's wrong in the other one. We can rename the other one in a minute as well. So expect that to be 5 cycles. And this is DEC Zero Page. So I think that's all we need for that one. And this is decrement value in the 0 page. Okay. So what's this one going to be? 0 page C6. Ooh, C7, don't want that. Right. Should have a single failed test for that. So I think I'm going to actually implement this first instruction 198. Yeah, I'll do the addressing mode because each one is basically a different instruction to the way we're writing it. So I'll do each one as I go. So let's see that I can decrement a value in the 0 page. So right. We have an addressing mode 0 page, which takes the cycles and it takes the memory. Gives us back a word address, I think. Yes, it does. So that's our address in the 0 page. Then I need to read a byte from the 0 page. Going to be our value, and then I want to add one. Oh, sorry, I'm decrementing this one, aren't I? Decrementing, which let's assume that takes a cycle because it's a math operation. I think that's going to take 1 cycle for the CPU to do that. And then we've got to write a byte. We've got a function for that as well. I'm going to write it back to where it was. The same value, cycles, at the address, same address, and the memory. Which makes you wonder where this value actually is living in the real processor. If it does do this and it's not affecting an actual register, because it doesn't say here whether it does affect a register or overwrites a register. If this magic value, where is that being stored? Is there an internal register that we don't know about inside the 6502? Maybe that's the case, but it might be that this is exactly what we need, but we'll find out that when we run this test. And it's not. What was wrong with that? Have I got this wrong in the test? I expect the 0 flag to be, 0 flag to be false, yeah, and negative flag to be false. Yeah, I'm not actually changing the so this is I'm calling this load register set status, but actually it's not a register anymore. It's just a value. So maybe that needs renaming as well. So this isn't load register set status anymore. This is, what do I call this? I think it's just set 0 and negative flags. I think that's a better name for that. Yeah, set 0 and negative flags from that value. Right, so that's made that pass, and it took the right number of cycles as well. Let's just check that we did that correctly. 5 cycles, yeah. So my expectation that this is taking a value is correct. I'd really like to know whether that does affect a register. It doesn't say that it does, but maybe that's a side effect that's not written down here, but it could be. Should we just do another one? Let's do another one. I'm not going to do as thorough tests as I did on the other ones on these, I think. I'm just expecting that this byte stuff wraps because we've got everything in a byte anyway. But if there's a different expectation, we'd probably have to put tests in after for that, I think. Let's just do a different one that's Zero Page X. So this one, we'll run the same test, except this time we need an X offset for Zero Page X. So let's do a 10 offset. And this Zero Page X is, yeah, the Zero Page address plus that value. So this is 42 plus 10. That is 57, so that should be the value we're looking for. I think this is a 6-cycle one, but other than that, everything else is the same. So it's just offsetting the Zero Page slightly on that one. So let's do that. D6. Okay, unhandled. Right, so let's implement that one. So it should be very similar to this one, except we're going to take an address from the Zero Page. We are going to add the X register to the address. Now, again, is it super clear what happens if this wraps or anything like that? I have no idea. I assume it does wrap, but does it say on here? Oh, the address calculation wraps if the sum of the base address exceeds. If we repeat the example. Yeah, okay, so we've done this before in another test, but our 8-bit registers do wrap correctly. So I don't think we have to worry about that. And we're going to consume another cycle for doing that. So I think that's it. Let's just see if that passes then. And it does, so I'm going to call that good. So let's do another one. So Absolute, this one's one of the easy ones where it just has a full 16-bit address. So it's very similar. Again, I'll take this one. We don't need to bother setting this X register this time. It's Absolute. And we need a full little endian address. So I'll go for 8000 again. So that's sticking the address 8000 after it. And at the address 8000, we'll put 57. And we expect that down here to be 56. And it's a 6-cycle again? Yeah, 6-cycle. So I think that is also a good test. So we're getting through these quite quick, but we are getting through them. And this one is CE, Combat Evolved. Right, does that give me a failed test? Yes, it does. Right, let's implement that one. So should I copy one of these? Maybe, yeah, let's just copy one of these because these almost do what I want. So this Decrement's memory absolute. So this time it's not the Zero Page, it's Absolute. Other than that, actually, that is actually the same, isn't it? Everything stays the same there. I think it does that. You can see where the extra cycle comes in there. Is it the extra cycle comes in over this one? Because it's got to read 2 bytes for the address instead of 1. And this one got an extra cycle because it had to offset with the X register. And this one doesn't do that. And then there's the extra cycle on the next one because of the offset of the X register. So I think that'll pass. Cool, so that one does. And same thing again, except with the X register this time. So Absolute X, Absolute X. So we just offset this with the X register. Let's put the 10 in there again. And I think, if I remember rightly, yeah, it's added to the full address, very much. So it's the same like the way the Zero Page one works. So this becomes plus 10, and down here it's plus 10. So I think that's all we need for that one as well. Yeah, looks like it. So let's put that one in. It's D. Failing test, yep, and we'll implement that one. So again, it's almost exactly the same as this one. I mean, we can just see what happens if you just paste that one in. In theory, you still get a failed test here. Yeah, and it tells you why, because it's read the wrong value. So that's just showing you that, you know, you can see how you can get these wrong. Again, this one just adds the X register and then takes a cycle using it, or doing it. Oh, did I get that wrong? What's wrong with that? Why doesn't that work? Oh, wait a minute. What am I doing here? Because I've got an absolute... Yeah, I've got an absolute X addressing mode. We've already done this before. We've also got a zero page X addressing mode. Right. Let's see what we get from that. Ah, that was it. What did I do wrong then? What does this do that I don't do before? Oh, because it's got this... Oh, this has got the weird... If it crosses the page boundary thing that we don't want. Do we want this 5? I think we want this version that always takes a cycle. I am kind of regretting this, like, taking cycles off as it goes, because I really don't know how the CPU works. So I'm really just kind of guessing. Is that correct? See, that one fails. So it's expecting, it took 7 cycles and expected 6. It feels a bit like, yeah, it's taking cycles to do that. It must take 1 to add the X on. And then does it not take 1 for the value? It feels really weird that it does this. It feels like it's 1 to take the instruction, 2 to read the address, then another one to read the byte, so that's 4, then another one to write the byte, that's 5, and then 1 to decrement the value, that's 6. Where does the 7 come from? Because there's... Oh, wait a minute, have I just done the test wrong? Yeah. Huh, done the test wrong. This makes more sense. Because it's 7 cycles, yeah. There we go. I was thinking that didn't look right. Yeah, that makes more sense that it's like that, that it always takes this, you know, 2 to fetch the word, 1 to do that, 1 to do the address, 1 to read the byte, 1 to decrement the value, 1 to write the byte. And that apparently is free. It's completely free. And it always has been. Okay, so that was a little bit weird, but... Oh, and you can see that those other refactorings that I've done on the other instructions haven't made them fail. That is decrement memory done. So we just need increment memory, which I believe is going to be the same. Yeah, so increment memory is going to be pretty much the same, except we're going to increment a value. So I'm going to take all these tests, and instead of subtracting 1, they're going to add 1. Right, let's see if that makes that compile. Should have 4 failing tests, which we do. So now we can implement all these at the same time, and I'm going to really cheese this again because I'm probably just going to copy and paste all these and just change them. Total cheese. And this is ink. Right, here we go. inc, and it's plus plus. This one's inc, and it's plus plus. This is so cheesy. Inc, and it's plus plus. Right, has that made our test pass? And the answer is yes, it has. That was super cheesy, but it super worked, because we're going for this giant switch statement method of doing this. But that is all, I believe, that is all the increments and decrements implemented. So that's another, how many instructions is that? And that's another 12 instructions done. So we are definitely getting somewhere. I mean, now I've got this, I can actually write a little program that increments and decrements memory. That would be really nice, wouldn't it? Maybe we should just, as a little toy thing at the end, let's just have a little go at that like we did. Yeah, let's write a little crappy program that can actually increment and decrement some memory and see if we can just get that to work. Just as a little test to see if what we've built even works. So this was our program that we had before. So we don't need to load the A register anymore, do we? Yeah, we do. We'll load the A register with 0. Load it with 0. We will. After that, we're going to store the A register at some 0 page address. That's the 0. So this is the, so that the hash means it's immediate. So this should be storing it at, like, let's store it at 42. So we'll do a 0 page version of this. Then we will increment 42. So 42 in the 0 page. And then we will just go round. Should we load the accumulator with the value from 42? Why not? And then jump back to the start. I think that will do it. I'll tell you what, we could load the X register with the value from 42, can we? And then we can increment the X register, which is in X, isn't it? There we go. So we were incrementing some memory, but we're also incrementing the X register with that same value, and then we go around. Yeah, that'll do something. It won't be very good, that, because it just keeps setting the X register then adding 1 to it. So it's not a great test, but should get the X register as 1 more than the value that we've just set into memory. And we go back to the start. So let's see if we can get that to work. So I'm going to open this in a hex editor. There it is. There's our little program. And I'm going to do the same cheesy trick that I did before. I'm going to replace the space with a comma, that. There we go. And we're going to paste that, and we're going to load a little program. So where's the other one that we did that loaded a little program? Load program tests. Here we go. Let's copy one of these. So test load a program, test load program that can increment memory. Just as a little test. Is that how we do that? We do it like this. And is there an easy way of finding out the number of bytes in an array? Can you do size of? Does that work? If that does that give me 1, or does that give me the number of bytes in that array? I don't know. We'll find out in a minute. Start address, and we'll keep executing that for 1,000 cycles. Let's see if this runs. See if it compiles. Well, it did. What is it doing? Just check that it got the, yeah, it got E bytes, so it wasn't 1, so that's definitely something. So that copies it into memory, and then we execute it. Sets the start address to 0, oh no, 1000, that's what we wanted, and then we start executing. So I think we had a function to just print the status of the processor after that. So let's just do that, and let's have a quick look to see if our looks like our processor is working. Oh, here we go. So, oh, because this isn't actually changing. Oh, it is changing the. Is it changing the X register each time? 54, 54, 55, 55, 55, 55, 56, 56, 57. Looks like we are incrementing the X register because we expected that to be like 1 more than the value that was in memory. And it started at 0. So that looks like that might be working. So that's just a good little indication that something's working there. Again, I might leave this test in. It's not super slow. I mean, you can't even tell. It's so fast you can barely even tell it's running. 1 millisecond. So really, is it the biggest deal in the world to leave that in there? Probably not. Let's actually just paste the program as well. And we'll just leave that in. But that's a good indication that, you know, this is, so that's code that wasn't compiled by, wasn't put in by me by hand. It was actually compiled by a compiler. So that's a good indication it's working. Because one thing that could happen with these is because I'm doing it like this, if this, if I put this value in wrong, if I change the value in here, these tests will still pass. I could change this to any random byte I wanted, like the opcode value, this value here. If I change the FE to something else, it would still pass, but that other program will start behaving weirdly. So that's a possibility. But at least by every now and again, if we're putting in bigger and bigger programs that can do more and more things, it's starting to get it better tested. So that's already a bigger program than we could have ever done before. Maybe because it's got, yeah, it's got load accumulator, store accumulator, increment memory, load X, increment X, and jump. So it's using lots of things that we've done before. That was quite quick as well. And we've got another set of these instructions working. So we're getting to the harder stuff now. I suppose it's the harder stuff because arithmetic's probably the harder one. Maybe the shifts might be hard and branching might be weirdly hard. I don't know, but we'll get to all this stuff in the next video.